All right, so I'm gonna go today quickly through my day 35. I continue reading this paper. I wasn't able to record everything that I studied today, but I guess it's okay. Yesterday, I believe I did the first 3 papers, and today I enter into the proof of the paper. As a quick recap, we have a scheduling problem. This particular problem, it's called PMP, process move programming. Looks something like this. You have some processes and some processors, and given an initial and final configuration, you want to determine 2 things. One, the subset. You have also 2 possible moves, so you want to move some processes to another to a target processors, and the way to do it is through migration or interruption, and you want to minimize the amount of interruptions you have. That's basically the whole intuition. And the main regarding the complexity is that they show in the paper that solving this problem is as hard as solving an NP hard complete. It's NP hard because it's as hard as solving the 3-partition problem. We know that the 3-partition problem is a NP hard problem, and I'm gonna show like some notes that I make. So at the beginning of the paper was the mathematical formulation. We know that we can prove that a problem is NP hard if a particular instance of the problem is also NP hard, and the way we do it, it's we have to take there exists like different types of problem, right? One type of problem is when you answer whether yes or no, like if a specific scheduling that satisfies certain conditions exist. This is, for example, it's called a decision. This is the decision version of the problem, right? So, for example, in this case, given the problem that is the PMP problem, we can create a decision version of the problem by asking ourselves if there exists a zero impact schedule. What is a zero impact schedule? It's basically an ordering of all moves such that you can do all moves as migration without no interruptions and never exceed capacity. So given this zero impact PMP problem, if we answer yes or no, whether we answer yes or no depends. What the claim is as hard as solving the 3-partition problem. That's the main point of this proof within the paper, right? And as a quick recap, the 3-partition problem is you're giving like some data, like some set, and you must split them into groups, and each group must have exactly three numbers, and the sum of the values of each group within the set must be W. So if this is possible, then it's 3-partitionable. That's like the definition of 3-partition. And the proof in the paper is that you can make a reduction of the 3-partition. How do they make a reduction? It's by showing a particular instance of the CIPMP problem. In this instance, it's a particular case in which you only have 2 processors, right? And you start one processor with some free space W and the other with 0 space. So it forced, if you want to move from A to B, then it forced that you have first move from B to A, because you cannot move from A to B if there is no free space. You must free W. You must move from B to A W space. So in this moving of weights resembles the 3-partition problem. That's the intuition. And when you make this type of proof, you have to take 2 things into account. That you have to prove them bidirectionally. So you have to prove that it works. If it's 3-partition, then it implies that it solves the CIPMP problem. And if it's CIPMP, it's then 3-partition. So it must be bidirectionally equivalence. And the way they solve this problem is by constructing this particular case of the problem, as I said. Then they assume that they suppose that exists a partition that can. So there exists a solution for the problem that satisfies partition, and then they follow the implications, and they also do the other way, in which they suppose that the partition does not exist, and basically you find that there is an equivalence. Hence, it's as hard as the NP-hard problem. And I think that maybe tomorrow or in a couple of days, maybe I give it a rest. I'm gonna check the proposition 2, and that was it for today.